Really? Yeah. Oh, if it works.
This one's currently muted, so you have to switch the button here if you want to unmute yourself. Here, if you switch the slide sound, thank you. Like, do we have to? Oh, it's on.
How are you? Okay.
Okay.
And then we can put that
Does this work? Yeah. Okay. Nice.
Yeah. I think this not, yeah, this not going to be used for that. Okay. I hope this is what they use like this.
I mean, I can also log in myself. I just didn't know what your setup is.
Yeah, that's the briefing on this.
I just wanted to check the Zoom session will run on this machine, or
No.
should I log in myself?
You know, you can just, you already have an account.
I think they will do this for you. Time. Did you actually show the time? How much time there is left?
Yeah, you have a timer on this machine. That will start as soon as you think. So you have 17 minutes and then 3 minutes of question. All right. And
You'll see the questions. Yeah, it's on this one, right?
Yeah. You already logged in. Wait, is the
So this will not screen lock, right? So
this is streaming, yeah.
yeah. No, there will be no screen lock or anything. So this will remain unlocked.
Yeah, I think all the. By the way, logged your password is.
Okay. Okay.
Yeah.
Oh, it's in the chat next to it.
I guess going to take your co-host, that should be I should make you co-host probably. Like if someone is like from the from the audience like has not muted their mic, then you can okay.
What means you make this machine in the co-host?
Yeah.
Okay.
Yeah, I think
Okay. Nice meeting you.
Nice meeting you too. I'm Contact.
Okay. How do I pronounce correctly? Antia. You sitting here or? Oh, no, wherever you like. Because I would also like to sit here. Yeah. I mean, they take a lot of overtime, but I think this is a started. All right. So welcome everybody to this session on microarchitectural leakage modeling. So I think some are still arriving, but we somehow have to get started also with this session. Otherwise, the next coffee break will be ultra short. So maybe we wait till, wow, okay, there's a big blob still arriving. All right, so nevertheless, we now get started. So we have the first talk, which is given by Jordi. He is talking about randomized caches and protection strategies there, and talks about a formal model there. So welcome, the floor is yours.
Okay, thank you. So this is a joint work with Oriol Farràs from Universitat Rovira i Virgili, Carles Hernández from Universitat Politècnica de València, and Miquel Morató and Batistas Costalabros from the Barcelona Supercomputing Center. So first of all, I'll divide this talk in, sorry, that doesn't work anymore. It's in 6 sections. In the first section, I'll explain what cache attacks are and what randomization-based protected caches consist on. Then I'll explain our model of RPCs and set associative caches. Then I'll give our main results, and then I'll extend these results to the pseudo-random and multi-epoch cases. Finally, I'll explain the performance analysis we did on our solution with respect to multiple rigging periods and workloads. And I'll conclude with some future directions. So first of all, in our setting, we can imagine 2 processes that coexist in the same machine, can be in the same CPU or in different CPUs. And these processes can access them the same memory, right? The same main memory. And it just so happens that because of the process isolation enforced by the MMU, it is fairly hard for them to know about each other, okay? If they are not intended to do so, right? If they are not intended to share data. So they use different memory blocks. And but unfortunately, well, we have caches to make things easier. So the main purpose of the cache is to reduce the excess latency of the data. So this works as follows. If some data is accessed, it goes always to the cache and it gets stored there, so that if at a later time this data is accessed, it can readily be fetched from the cache. And there is no need to fetch it from memory, thus reducing the latency of the access. This is very good for performance, but for security is disastrous because it reveals the access latency to processes. And this reveals if data is already cached or not. And so a process can distinguish between this case and this case. In this case, we say that it is latency 1 because there is a cache miss. And otherwise, it is latency 0, right? There is a cache hit. So this can be used in an attack setting to recover cryptographic keys, for example, in an AES implementation or in many other settings. So what one does is first the attacker somehow fills the cache. Here we are assuming a fully associative cache, which only consists of 1 memory, so something really simple, like in this picture. And the attacker fills the cache with some data that he knows is in there, then waits for the victim to perform some kind of activity, maybe signing something or using a cryptographic key. And this data the victim accesses will inevitably evict some of the data from the attacker because the cache is full, right? So at a later time, the attacker can re-access her data, only to see that some of the data was evicted. And so she gets some kind of information from external processes, thus breaking this process isolation. Well, to prevent these attacks, there are several mechanisms proposed. And one is randomization-based protected caches, which consist in not letting the processes access the cache so directly, but putting a cache randomizer in between to randomize the accesses and the addresses, sorry. And we call this set of cache randomizer and cache a randomization-based protected cache. So in this work, we aim at studying the security of these mechanisms against single target access-based attacks, that is attacks that only target a single victim address and use only latencies, and only in the LLC, so only in one large memory. And this englobes security against spam and probe. The thing is that in the literature, several previous RPCs have been broken. And so we try to address or mitigate this kind of break and repair cycle, and also analyze the impact of existing attacks. And to do so, we take a provable security approach, where we first model mathematically RPCs, then we give security definition and security proofs, and afterwards we analyze the performance of our solution with respect to different rigging periods. Now, admittedly, there are many other side channels and abilities that we didn't look at. So one can use flashing, timing, external processes, use the cache, the whole cache hierarchy instead of only one memory. We only looked at attacks that use latencies. And for these attacks, there are three kinds of mitigation strategies proposed. One consists in partitioning the cache and letting only one process access one partition. The other one is a kind of very stateful randomization mechanism that works for small caches. And we stick to the randomization-based protected caches for efficiency reasons. So now our model, I'll explain what set associative caches are. So set associative caches are organized in S cache sets, 1 to S, with A lines each, which is called the associativity of the cache. And also they have an inherent representative policy RP. So they address to via cache addresses, which consist of a set index that takes values from 1 to S and directly correlates with these cache sets, an attack that ends up stored in one cache line on an access. So I'll illustrate now the previous access-based attack for this model. So first of all, if the attacker wants to monitor cache 2, she issues the address 2T1, and this tag ends up stored alongside with the data in reality, but we omit the data. And what she does is to fill somehow this cache set. So this can be done with latencies. There are attacks that are published that do just that. And the attacker at any point can make sure that nobody has touched this cache set because the latencies return 0, right? Now she waits for the victim to perform some kind of activity, and then she can reaccess the previous data only to find that some of the latencies are 1, and she knows that the victim accessed cache 2. So to prevent this, we said that we would add a cache randomizer to randomize cache addresses, and this has the effect of scattering accesses throughout the cache. That's a very efficient way of doing this. So access-based attacks should be harder. The question is how much hard. And to randomize addresses, we only randomize in our work the set index part of the address using the whole address to randomize it. And also we model cache randomizer as pseudo-random function, simply consisting on an algorithm rekey that generates new keying material from previous one and so on randomness, and also on a cache randomization function pi sub k. Now I'll give our main results. Well, the thing that happens here is that even with these mechanisms in place, there are some articles that have been found attacks that succeed in breaking security with arbitrarily high advantage. So given enough cache accesses. And what RPCs do in this setting is establish a rekeying period, which is nothing else than a number of accesses, after which the key is renewed and the cache is flashed so as to not have any stale data. So this establishes a number of accesses in which attacks should take place. And we treat this rekeying period as the security parameter of RPCs. And so up until now, this rekeying period has been set purely heuristically, so to thwart existing attacks. And these, as attacks have been getting better and better, this has led to insecure RPCs. And so we ask our first question, that is, can we provide provable security guarantees for some of the rekeying periods? And our second question is, okay, even though the key changes, the cache randomizer doesn't. So Bouja et al. In their CASA article showed that this information can be exploited. And the second question is, can we provide security across different epochs, probably? So just to be clear, instead of looking at particular attacks, we look at all attacks that conform to our security definition, that look only at one target address and use only latency information, and are considered to succeed if their advantage crosses some threshold P, for example, 1%. And this approach allows to provide concrete security guarantees and analyze existing attacks. So this is the security definition, game-based security definition. So first of all, the RPC is flashed and rekeyed. This is the start of an epoch. And then the attacker prepares the cache with N1 accesses. Then the victim generates a challenge bit B, and if this B is 1, performs the access, and then the attacker just issues N2 accesses to see if something has happened, and issues a guess B prime for the bit B. And we say that the RPC C is N access secure with advantage at most P if anywhere this targeted guess is inserted during this game, and whatever it is, no attacker has more than P advantage in guessing this challenge bit. And so to analyze the security with respect to this definition, that's a very standard way of proceeding in cryptography, we used an ideal cache randomizer, which is nothing else than a random oracle for functions from addresses to set indexes for cache randomizers. So using this, we obtain that for every threshold P, this ideal RPC is N access secure with advantage at most P for this N here. So we can compute this N, this kind of truncated binomial distribution given P and the cache parameters. And for this N, no attacker will succeed with more than advantage P. This is very nice. So this has been slightly improved with in a scenario with noise. And to put an example, we consider the LLC of Coffee Lake, which has associativity 16 and over 12,000 cache sets. And suppose we have the advantage threshold 1%. So we put P equal 0.01, and we see that if we set the rekeying period to over 100K, no attacker succeeds with more than 1% probability. This is amazing. This is a concrete value for the security parameter, let's say. But of course, we have a problem. 2 problems, in fact. The first is that no ideal cache randomizer exists in the world. And the second is that an attacker will not just attack for 1 epoch and then forget about us, right? They are more vicious than that. So, so in the first case, we use pseudo-random cache randomizer, which are very standard in cryptography, PRFs, just consist on a if you have this experiment where you either feed the distinguisher with new evaluations to either a random function or a pseudo-random function, this distinguisher outputs a bit B to say whether we are in one case or the other. And the cache randomizer is nu epsilon pseudo-random if it is epsilon hard to tell apart these new evaluations from random, right? And we get the following reduction. So if the ideal RPC C is N access secure with advantage at most P, and the cache randomizer is N epsilon pseudo-random, then this new RPC is N access secure with advantage at most P plus epsilon. So this is the trivial reduction, let's say. And for the multi-epoch case, we have this framework by Abdal and Belare from the 2000s we use. So the victim starts with a challenge bit B, and then the attacker and victim engage with R copies of the previous game with this challenge bit. The attacker outputs a guess. And again, we say that the RPC C is R epoch and access secure with advantage at most P if whatever these target addresses are and wherever they are inserted throughout the games, no attacker succeeds with more than P advantage. Following up the Belare, we analyze security, and the result we get is the following. So if this rekeying period N guarantees security for the original RPC C with advantage at most P, and rekey is R epsilon pseudo-random, so in R epochs, rekey is used R times, then this C is R epoch and access secure with advantage at most R times P plus epsilon. This is to be expected. Advantages are just summed up, so this result is no surprise. But what is nice is that rekeying has the effect of expanding the time window where security is probably enforced. So rekeying works, and that is why people use it in reality, but this works theoretically also. So suppose again that we want to sort attacks with an advantage bigger than 1%. If we have a cache randomizer that is epsilon hard to tell apart from random, 0.001 hard to tell apart 100,000 evaluations from random, then we get the rekeying period a bit less than 100,000 accesses. So here we have a computational security thing that, of course, reduces the number of accesses in an epoch. And for the multi-epoch case, assume we have a rekeying algorithm that is this much pseudo-random. We see that we can extend this security to 9 epochs of considerably less accesses per epoch. So this has an impact on performance, but the security is probably enforced for more than 5 times the original amount. So this is very interesting. Finally, we did a performance analysis of our solution using ChampSim to simulate the coffee lake LLC with this cache randomizer, L1 and L2 private caches, the pseudo-random LLU, the pseudo-LLU represent policy, and these workloads. And here we see a graph for the IPC for a randomized cache, normalized to a non-randomized setting. With respect to different workloads and rekeying periods, we see that for some workloads, the impact is reasonable. There is one workload there above that actually benefits for the randomization, which is remarkable. But in general, the impact is not huge. So as for conclusions, we provide a security model for RPCs. We present this game, these security definitions. We give recommendations on how to design the parameters of a cache to obtain provable security guarantees. And we provide a performance evaluation. And as future research lines, we would have to study additional hardware techniques, such as skewed caches, time to live features, other kinds of rekeying that exist in the literature, measuring for example, the evictions instead of the accesses, right? And see that some of these mechanisms would give better security or would allow for a provable security approach. Then the next point would be to broaden the scope of security definitions. This security is very strict. It only captures attacks that target a single target address, that use only one memory in the cache hierarchy. So extending this to more general cases where the attacker has other capabilities like flashing, for example, would be great. And finally, tightening the bounds for particular represent policies. There are some results in our article that can be improved considerably for the random policy, for example. So it would be interesting to do that also. And that's all. Thank you. I'll take any questions.
So thanks for the nice presentation. So are there any questions? Yeah. So you can have my micro.
Fantastic. Thank you. Nice talk. I was wondering, so in this work, you went from a rekeying period that you need to select, provably to an advantage. Okay. Do you have some additional insights in what a good advantage would be to thwart the attacks we've seen and maybe see in the future?
What a good advantage would be?
Yes.
So in practice, how you would come up with an advantage that would, I mean, as smaller as you can, right? Yeah. So I don't know. I mean, this advantage is like the probability of an attacker distinguishing the challenge bit. So distinguishing if an access has been done or not by the victim. If it is smaller, the smaller the better, for sure. But this will impact inevitably the performance of the solution. So you will not have an advantage 0 for sure, because that's
right. But this is a new parameter that needs to be selected, right?
Yeah.
Okay.
Well, it's not new. It exists in the literature. Every RPC does that because, as we've shown in the ePrint version of the article, if you imagine an attack to an RPC with infinitely many, let's say, accesses, you will have as much advantage as you want. So yeah, it's you can have arbitrarily high advantage to break an RPC given enough cache accesses. So yeah.
Okay, thank you.
Other questions? Yeah, so I actually also had a similar question in that direction. I mean, in the end, the question is whether you put the P, right? The probability. You in your example, you always had this 1%. You in the end need to map it then to an attack. It's always this trade-off you have to do, right? In terms of the attacker will eventually be successful at some point, no matter
Yeah.
where you put the parameter. And then the question is what a practical value is. That you actually take the risk in terms of saying, okay, I pay that much performance or not.
Okay, I mean, that depends on the application, I guess. If I were to say that, you have to say for how long would an application run to be able to give a concrete parameter.
So you don't have a general rule on that.
No, I don't. I mean, it depends on the security evaluation of the environment you have, and it's something that a designer should choose. Yeah. But I mean, this is the case for cryptography in general, right? So, yeah. Well,
yeah, maybe also a question related to that in your evaluation section where you evaluated the performance. So I didn't look in detail which benchmark was what. So essentially the memory intense applications had, or the memory intense benchmarks had then the lower performance, right? Or
sorry, what's the question?
So there's a difference performance impact on the different workloads you had.
Yeah.
So this is those that have a significant impact, I assume. So these are essentially the ones with a high memory.
Yeah,
that are memory intense applications, right?
Yeah. Those are the ones that are impacted by the rekeying, the flashing of the cache. It depends very much on the workload. For example, this kind of workload benefits of rekeying because it accesses the cache in a particular way. So rekeying actually scatters the accesses, and this is better. But if you scatter the caches for some applications, that's actually detrimental for performance because there are many more cache misses, right? So that's the problem. This workload would in a normal setting does a lot of cache hits, so the cache helps a lot. But in this case, the cache really, yeah, okay, it's thanks. That's it.
Any other question? If not, then let's thank the speaker again. So we move on to the second talk. All right, so we now move from timing to power analysis, and we will now hear a talk by Pantea on actually analyzing or pinpointing power side channel leakage in SOCs.
Thank you. Can you hear me well? Is it good? Okay. Hello, everyone. I'm Panta Kiai, and I'll be presenting the paper SOC root canal, which is root cause analysis of power side channel leakage in SOC. This work is a collaboration with my PhD advisor, Professor Patrick Shaman from Worcester Polytechnic Institute in Massachusetts. So in this talk, I'll first talk about challenges that we faced in protecting SOCs or system on chips against power side channel attacks. And then I'll give a very short and quick comparison between post-silicon and pre-silicon evaluation or assessment of power side channel leakage of a design. I'll talk about two examples that show different things that can go wrong in a design and cause side channel leakage, specifically power side channel leakage in an SOC. And finally, I'll talk about our tool, which is called Root Canal. that can automatically find causes of power side channel leakage in an SOC. Once we're talking about, or once we're dealing with an SOC or system on chip, we have several abstraction layers in play. The highest abstraction layer will be the software layer, which will be written, the source code will be written, the libraries will be included in that code, and finally we'll have a compiled binary file that will reside on our processor and will run through it. We also have what's called instruction set architecture, or ISA for short, that basically abstracts away the details of the hardware implementation, but gives programmers some information about what is going to be finally in the assembly code that they write. We have then the RTL of the hardware, which is the abstraction layer at which a hardware designer will describe their circuit fully in a human readable language. And then that will automatically be transformed into what we call a gate level netlist, which will basically map the RTL design into the algorithm that only uses the library that we provide the synthesis tool. And finally, we'll send that netlist for fabrication. Now, specifically in power side channel leakage, even though we have all of these abstraction layers, the root of the attack will always be at the very lowest level of the hardware. But the cause of the attack can potentially come from the software. So it can be from basically any layer that is happening between software and all the way down. And what I mean by the cause of the attack being in the software, for example, is that the software can have a secret data that then it will consume some power just to do some computation on that data. And because of this correlation between that secret data and the power consumption, an attacker will be able to analyze the power consumption, gain information about the secret data. Now, our goal in this work was to find the root cause of any side channel or power side channel leakage that we observe. And because the root is always at the hardware, that's where we're going to start. So we will start from the hardware. Specifically, we chose to do it from the gate level netlist. So we find at the gate level netlist the gate that contributes the most to any leakage that we observe. And then we try to go up this levels of abstractions all the way up to the software, and then point out exactly which instruction from the software is causing the leakage that we observe. Now, I'll compare post-silicon and pre-silicon evaluation of power side channel quickly. So traditionally, how we would end up with a secure enough in terms of power side channel leakage design was that we would start with the RTL of the design. We'll go through the entire design steps, both front-end synthesis and the back-end flow of the design. And then we will have the GDS file that would be taped out. And once we have the taped out chip back to us, we would have to build its board and wire bond it to the board. And then we would be able to, only then we would be able to do some power measurement. And then on those measured power traces, we would be able to do leakage assessment. At that point, though, if we find any leakage, we had a leaky design, so we had to fix it for the next iteration of our design. But we could only guess or make some educated guesses about what could have caused any leakage that we saw. So we should have just basically guess what has caused the leakage, then go back to our RTL or the gate level netlist, try to fix that problem, and then go through the process of taping out a chip and then testing it again and again. So this loop consists of potentially several iterations of tape out of a chip. In pre-silicon, we try to take this tape out of this loop. So what we do in our work is we start from the RTL. We do the synthesis to front-end synthesis to get the gate level netlist. At that point, we stop the next steps of the design, which is the back-end design. We don't go through that yet. On that gate level netlist, we try to simulate power traces for the test vectors that we want to run to find any bugs in our design. And then on those simulated power traces, we would do some leakage assessment at the gate level. And because this is then done in simulation, theoretically, everything is known to us. So at this point, if we find any leakage, we should be able to find also what exactly has actually caused that leakage. So we do that. So with much more confidence compared to post-silicon, we can find out what has caused the leakage that we observe, and then we go to fix it in our design. And we do this iteration multiple times until at the gate level, we don't see any leakage anymore. Only then is when we move on to the backend flow and we tape out the chip. So if we compare pre-silicon with post-silicon, pre-silicon will save us time and money because we don't have to tape out the chip multiple times. But also we can be confident in finding the correct root cause of the leakage that we observe. So in the next couple of slides, I'll give 2 examples of what can go wrong in an SOC system that can cause or lead to leakage. The first example is when a compiler optimization would cause power side channel leakage. And the example that we look at is ISW multiplication, which if we just look at the C code, it makes sense. It should be correct. We don't expect it to have any power side channel leakage. But once we compile it, and we compile this using the RISC-V GCC compiler, there is a reordering happening here that this will lead into power side channel leakage. And we simulated this code running our processor, RISC-V processor. We simulated about 1K power traces and did run a TVLA test on it. And as we see as we expect, we see all these leakages happening. So this is an example that if we only look at the C code, which is what the designers are developing, we don't expect to see any leakage, but because of all the automatic tooling, until we get the binary file, the leakage is observed. The next example is when the interaction between hardware and the software together in an SOC cause a leakage. So if we look at the hardware separately, we don't expect to see leakage. If we look at the software separately, again, we don't expect to see any leakage. And for that, we look at an example of a byte masked software AES. So just at the C code level, we didn't expect to see any leakage, but when we simulated some power traces and ran a TVLA test on it, we saw leakage in every round of these 2 loops that we had. And these are the outputs of our root canal that I will go over in the next slide. But basically what they mean is for each instruction in our assembly code, it was able to point out which pipeline stage is showing leakage. We had fetch, decode, execute, memory, and write back stages. And here the blue font is showing the leaky stage of the pipeline in this loop and in the second loop in our code. And once we also look at what is causing this leakage, we see that in our specific implementation of the SOC that we had. In the bus interface, there is a storage element. There's a register that basically stores every write to the memory before that data goes to the memory. And so here, basically what's happening is in like consecutive iterations of these 2 loops, what's happening is shares of the same variable are overriding each other in this register. And so there is unintentional on-masking happening because of this storage unit register that we have. So all of these examples show that there are several things that could go wrong in the software, in the hardware, or in the combination of the 2. So it's very important to have a unified tool that can automatically detect anything that can go wrong. So find the leakage, but also find the cause of the leakage, because we need that to know that cause of the leakage to then be able to fix it. And we have to be able to do so independent of what the source or the source cause is. It can be from the compiler, from the C source code, from the architecture, from interaction between hardware and software, or anything else. Root canal tries to do exactly this. So it finds where leakage occurs first at the gate level netlist in terms of exactly pointing out what gate is leaking, and then goes up the hierarchy to also point which instruction has caused the leakage. and it's independent of the real cause of the leakage. So how it works is, so we have a software that we want to run on this SoC. We have to compile and load it to the RTL of the hardware. Then the RTL will be synthesized and simulated. This simulation is to have some simulated power traces, and we will have a simulated power trace for each test vector that we run through our system. Then we have a step called ACA, which is short for architecture correlation analysis. This is one of our previous works, so I won't go over all the details, but at the output of this, we will be given the leaky gate cycle tuples. Basically, ACA will tell us which gate is leaking and at what clock cycle it is showing the leakage. Root canal then takes the output of ACA, and for each leaky gate, it will first recognize if it's from the inside of the processor core in the system. And if so, it will tell us the leaky instruction. And if it's not from the inside of the processor core, it will tell us which hardware module or hardware unit it is coming from. And it specifically works in 3 steps. The first step is basically the ACA step. It needs the RTL, the software code, the technology, meaning the library files and all the technology node that we use. And also a testing strategy. That testing strategy can be, for example, a specific TVLA test, non-specific TVLA test, or any other test that we want to run. Then this step will give us the leaky gate cycle tuples. Second step, it will try to find out exactly where each leaky gate resides in the netlist. To do so, it will first transform our netlist or gate level netlist to a graph, and then by doing some analysis on that graph, it will tell us for each leaky gate, the leaky unit, which is the hardware unit that the leaky gate resides in. And if that leaky unit is from inside of a processor core and the processor core is pipeline, it will also recognize which stage of the pipeline it is coming from, and we will call that here the leaky stage. Finally, if that leaky unit is from inside of a processor core, meaning we have that leaky stage, we will have step 3 that will tell us eventually what the leaky instruction or the cause of the leakage from the instructions is. And to do so, step 3 will take the leaky stage and the leaky time. The leaky time comes from the leaky tuple from output of the step 1. It will look up the log of instructions for each stage of the pipeline. And basically for the log of instruction for the leaky stage, it will look up the instruction that was running at the leaky time, and then it will tell us the leaky instruction. So in this paper, we had 4 different examples. I'm not going to go over all of them. I just want to point out if we only take the leaky gates into account, we'll end up with too many gates to make sense of when we have an order of thousands or hundreds of gates. It's very hard for an engineer to understand what was going wrong. But if we can traverse up all the levels of hierarchy all the way up to the software, then we'll end up with only a handful of instructions. And so it's much much easier for us to understand what is going wrong. And then finally, the execution time. In the paper, we show the execution time for each step of root canal. Which first we have the synthesis. It just depends on the design size, and it was actually the same for all of our 4 examples. Then we have the simulation and power simulation. This depends on how many test vectors we have, basically the test bench length, as well as the size of the net list, because it has to do all these measurements for all the gates in our net list. Then architecture correlation analysis, which depends on netlist size because it has to correlate each gate with the leakage, as well as the trace length and the leaky samples because it has to correlate them with all the leaky samples. And then the back annotation step to find out where each leaky gate resides. That also depends on how many leaky gates ACA found, as well as the netlist size, how many gates we have in total. The reason for that is the complexity of our graph depends on the size of the netlist. That's why the runtime of back annotation depends on the netlist size. And so if we look at all of these total execution times, and I have to point out example 3 was 3 different tests accumulated here. We see that it takes less than 24 hours for us to capture bugs, and it might look like a lot, but if we know what we're replacing and in which case we're trying to replace a post-silicon evaluation, which will take months to perform, we have a pretty good execution time. And we can actually point out to the exact cause of the leakage from any abstraction level. So to conclude, when we have SOCs, there are a lot of abstraction layers. So it's just are a lot of things that could go wrong in a design to make it buggy or leaky in terms of power consumption or power side channel leakage. And we have to take care about all of those abstraction layers and the interactions between them when we want to protect them against power side channel attacks. And root canal can enable root cause analysis of power side channel attack for SOCs in both hardware side and their software side and the interactions between them. Thank you so much for listening. I'll be happy to answer questions.
So thanks for the nice presentation. So are there any questions? Yeah.
Okay, thank you for the presentation. I'm not sure I understand what is the gain for you to go down at the gate level. If you are interested in the instruction and if you already have like the power trace and the TVLA, from the list of instruction, you should be able to just, and like where the leakage happened in the trace and the list of instruction, you should be able to know which instruction caused the leakage. And I don't really understand why you go down to this gate level before coming down to the instruction. Because I think there was another tool, I think called ROSA, which was doing just that, like from the simulated power trace to the instruction without going down to the gate level.
So are you saying, why don't we just look at the assembly code and find out? Yeah, we can do that, but then we will only be able to find out if at the instruction level something is wrong. For example, the second example, we couldn't find out about the leakage just from the assembly code. We had to have information about the architecture design as well.
I think it's right back of the second shell that was created unit. So at this point, you kind of first bit of this, getting this kind of leaking and then writing back the second shell, but you could already.
So there is some manual effort there, though. It's not automated. So to make it automated, exactly because of this, to make it automated, we started from basically what is the root of the leakage, and then we tried to go up.
Thank you for the talk. I'm curious, how did you model the power side channel signal? What tools did you use? And also, did you consider electromagnetic side channels?
That's a very good question. So for us, we just use the CAD tools that do basically estimate the power consumption of a design, but we did that in like more finer granularity. And for EM, we didn't do anything in this work, but if we want to do the exact same thing there, we might need some, again, simulation tools to do the EM. But EM also has the more complex feature that it also depends on the area of the location of a probe. So we have to take that into account, but we didn't look at it in that work.
And to follow up, did you do any tape outs and correlate back to the simulation, like that
Yes,
it's
that's
actually
one of
accurate?
the future things that the group is working on.
Okay, thank you very much.
Thank you.
Hello. So it seemed like even though you're able to, get results much faster than you would if you're doing an actual tape out, if I have to wait 24 hours to get my post-power simulation results, that's still quite a long time. Would your tool still work if you worked on pre-synthesized netlists? So if you're just working on the sort of functional RTL post-simulation and you approximated power consumption by looking at Hamming weights and just toggles, would that still work if you were able and be faster if you're willing to accept the loss of accuracy?
Potentially, yes. Well, it will work in terms of just at the behavioral level. But if that actually maps to the final gate level netlist depends on the optimizations that the synthesis will do. So it will not be perfect or as good as this.
Would that be a useful thing to look at in future then to
Sure,
see if
yeah.
there's that correlation there?
Yes, but I think it becomes more of a problem than optimization of the synthesis tool than how this tool will work.
Thank you.
Thank you.
Another question in the
May I?
front?
Small question. How many traces do you typically need for the simulation to get concurrent like results from the t-tests?
In some cases, we did 500 and sometimes 1K. Because it's a simulated environment, we don't have any measurement noise. So it's much less noise, so much less power traces are required. Usually maximum of 1K is enough.
Thank you.
May I?
There's another one.
Stefan, may I also ask a question here?
Yes, my question would have been, how do you model this, the pipeline of the processor, and how easily can this be adapted for a different processor design with a different pipeline depth?
I don't see the. Could you repeat that? Sorry.
How easily can your framework be adapted to a different processor pipeline, and how do you model that in your framework?
So if we have, for example, if we don't have any pipeline processor, if it's a multi-cycle processor, here we will just, work with it as if it was another hardware unit. So we don't think of it as a processor anymore, because at whatever cycle the instruction is running there, at whatever cycle, there's only one instruction running there. There's not multiple instructions. But if there are more, then our graph will become bigger. And so the analysis on that graph will become more complex. I hope it answers your question.
May I follow up on that question? That was very interesting to hear. But did I understand correctly? You have a single stage CPU there without any pipeline. There's always one instruction in there. Does your framework extend to these CPUs which have multiple instructions in the pipeline? Say two execute stages and a write back, something more complicated. What would you need in terms of annotations there to support this?
So in terms of this tool, it doesn't change much in the concept of this tool. It just becomes, the analysis becomes bigger, or the scripts will become bigger to find out where everything is located. Especially because what we lay on here in the, what we rely on here for the netlist graph analysis is the pipeline registers. And our simplest idea is any gate that has inputs from stage I plus I minus 1, outputs only to stage I. We know it's in between these two pipeline registers. But there are like forwarding paths and a lot of other things that only exist in more complex processors. Some of them existed in our 5-stage pipeline processor, but if we go to I don't know, more complex processors with 7, 9 stages, that will become maybe more complex. And that's what makes this step more complex as well. But the idea of it is still going to be similar.
Thank you.
Thank you.
So we're already over time, but there is one online question. I just shortly pose it because it's just a few minutes, seconds, I guess. So the question is just, whom do you expect to run this tool? Whether it's the chip manufacturers, the users that then send their code to the manufacturers. So who's actually the user of the tool?
The user should be potentially the hardware designer, but they also have to make sure about basically the secure software that will go through that system. They have to include that in their tests as well, because we can't separately analyze the hardware, separately analyze the software, and make sure they're secure when they're gonna run together. So we have to have access to both.
Okay, so I think we have to take the rest offline. So thanks for answering all the questions, and thanks everybody for this session.
You can stop the recording. Yeah. Yeah. You can stop the recording.